Hey everybody, today we have I guess you call it a slightly offbeat probability problem where we're actually trying to calculate the probability that a randomly selected positive divisor of 24,024 has the form PQR where P, Q, and R are distinct primes, okay? Now in order to do this, you need to know the prime factorization of 24,024. It allows you to count the divisors very easily. Now just to make sure, just a simple example, 4 times what 6,006, that's a pair of divisors, right? It's a pair of divisors. It's equal to 24,024, right? So that's a pair of divisors, but we need to know all of them because counting is a big part of probability, and so you need to know how to count. And you have this is an example of 2 of them, but we need to count all of them, so that's the point. Now knowing what the prime factors of 24,024, that's important. This is a divisibility test right here. Let me just write this briefly here. I proved this in a video, it's been quite a long time ago. But this is a divisibility test for 7. Okay, and the idea here, and you can see what's going on here. The idea is fairly cool. It's not a very well known one, I guess, but notice how we have 2402 in both places here. So we chopped off the 4, but we subtracted 2 times 4 from 2402, and you get 2394. Okay, now it's not immediate whether or not this is divisible by 7, but so you just rinse and repeat. Notice how you chop off, and all you have is 239, and then you subtract, and you get 231. Which is not too hard to do mentally. 231 is equal to 33 times 7. So the 231 is a multiple of 7. Ergo 7 is part of the prime factorization. Now it's real easy to see that 2 is a divisor, and also the sum of the digits here. Sum of the digits is 4 plus 2 plus 4 plus 2 is 12 is divisible by 3. We just did it for 7. There's also, it's divisible by 11 because these alternate. They alternate in a negative sort of fashion. They sum to 0, so 11 is. I don't know that any. I did one a long time ago for 13, but in any event, you have to come up with this prime factorization by hook or crook. Okay, this is just a little bit of help in that direction. So it is rather time-consuming to actually do this, especially the larger the constant. Okay, but anyway, we do have a prime factorization of the only constant in the problem. And we're going to use the fact that probability is defined to be the count of desirable outcomes over the total outcomes. The simplest example, you toss a coin. What's the probability you get heads? Well, there's 2 possible outcomes. There's 1 favorable outcome. So it's 1 over 2 is 1/2. That's a very simple example of how probability is defined. Okay, probability is always going to be a number strictly between 0 and 1. Now, so we're going to go ahead and adapt that to our problem statement. So we have to count the number of PQR divisors. Now, y'all, just a quick example on that. An example of a PQR divisor would be 2 times. That's the smallest one, in fact. 2 times 3 times 5 is the smallest PQR. This has an OES article about it, actually. All of these things do. But is that right? 30 is equal to 30, right? Okay. So that would be the smallest PQR divisor. And it's pretty clear that's not a divisor of 24,024. But we need to be able to count them some way, okay? So one way to do this, it's really quite simple. If you've had any discrete math at all, this isn't so bad. You use something called the combination formula. You come up here and you note that you have 1, 2, 3, 4, 5 distinct prime divisors. It doesn't make any difference about the exponent, as you'll see. So if we need to count the number of those, that's the same thing as selecting 3 marbles out of a bag of 5 marbles, which is a super well-known interpretation of the combination formula. So what we end up with here is 5 choose 3. And a check to see if you're doing this right, you want the number in the numerator to be smaller than the number in the denominator. Now, as far as the count of the 24,024, the approach here is to consider the exponents and understand that some of the divisors would correspond to an exponent of 0 when you broke this thing apart, right? And so what you can do, you can actually just increment each of these exponents to account for the potentiality of 0 being an exponent, okay? So what you get right here is 4 times 2 See, 1 plus 1 is 2, and 1 plus 1 is 2 all the way across. How many of them are there? 4. So you got this happening. Okay, folks, like that. Now let's carry on with the mathematics here, or the arithmetic. The way to write 5 choose 3, at least the way I've always taught it, is just to go like this: 5 times 4 times 3, meaning you start at 5 and work your way down decrementally 3 times. Okay, so you get 5, 4, 3, but then the other result, other part of the combination formula is to put 3 factorial right here. Okay, now this number right here is 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th, which is 64. Right? And so, folks, what you end up with here, notice that this top part is 60. 3 factorial is 6. So you end up with 10 over 64, which reduces to the fraction 5 over 32. So that is the probability if you randomly select a divisor from this large constant. What is the probability? It will be the product of 3 distinct primes. And y'all, this would be a pretty easy, let me go ahead and circle that. This would be fairly easy to do in Python or C or anything. You can just do a loop, and you don't have to know any results at all. Just you can go through, I'm sure there's a Boolean divisor function in Python or anything, C++. And then you just keep a count. And also you can, let's see, I guess it would be a little, I don't know. But you could just check, do some kind. You could write some kind of function that would check to see if the divisor was a product of 3 distinct prime divisors. Maybe that'd be a little tricky. But you could do this by brute force to see if that happens. Relative frequency 5 over 32, or absolute frequency, whatever you want to call it. But it would be a fun program to write, in my opinion. But anyway, that's the end, folks. Thanks for viewing.